Imagine having all your data at your fingertips, no matter where it might be stored, on-prem, in the cloud, anywhere on Earth. That's the vision of Hammerspace, a company that's pioneering the world of parallel file systems. Just like magicians pull rabbits from hats, this technology is revolutionizing the foundation of our information economy. Find out more on this episode of Future Proof.
The future is here already. It's just not evenly distributed. Yet. Today's world teems with innovation. The nexus of hardware, software, and human ingenuity promises a revolution in possibilities. What does tomorrow look like? Witness Future Proof.
Today, Hammerspace announced a new innovation in our data platform. And before we jump into what that is, I want to just give everyone a quick kind of high-level overview of what problems Hammerspace has tackled and kind of why we've done it. So if you think about the last 10, 20, 30 years, and Eric and I have talked about this on my Data Unchained podcast, and you think about what we've been doing, the architectures a while back over the last couple of decades were really designed for the storage system owning the data and dictating how it's retained, protected, and anything that was done outside of that was done outside the storage system, which meant you had to make a copy of the data to move it to another application, make a copy of the data to get it into the cloud. And that really created not just copy proliferation, but users didn't necessarily have access to or visibility into all the data that existed as it became increasingly decentralized. And so with Hammerspace, a kind of core innovation we had was moving the file system up the stack. So instead of embedding it in the storage system, in the storage hardware, we've raised it above the stack so that when users and applications connect to their data plane, to their file system, they just do that once. And if additional data sets are added, if additional data locations are added, different storage tiers are added, given if the user application has the permissions, they can immediately see all of the data in their global data environment. And so that gives visibility to the entire data set on a global level in all different types of storage environments and storage tiers. And then when the data needs to be moved, we aren't making copies. We aren't adding to this problem of copy proliferation. Instead, through intelligent automation, it is placed where it needs to be used. So if you have remote GPUs or you're spreading your data across compute clusters, the data is automatically orchestrated to the compute. If you need to tier it for disaster recovery reasons or lower cost storage reasons, that's also automated, but what is done under the file system so that the users and applications have a persistent view to their data, even if it moves around. They can still connect to it, they can still see it as just a file directory path on their computer, and it doesn't disrupt their operations. And then underneath that then comes the storage system, and the storage system that is already in place or new storage that needs to be added can automatically be added as capacity or performance into that global file system, again, without disrupting workloads or users. So what that ends up looking like from a Hammerspace perspective is all the things that you need are buried underneath the global file system. That's a parallel file system. So you have the ability to deliver those HPC types of performance with metadata taken out of the data path. So you have a really high performance parallel file system storage infrastructure. Underneath that, if you have enterprise features that you need to take advantage of, to protect against ransomware or, encrypted data, be able to audit what's happened with data as it's moved around, that's all built in. And then, as I mentioned, the automated data orchestration makes it possible that as data needs to be moved for any purpose, whether it's to get it local to compute or for storage reasons, that's all done transparently to the user. And so I bring this all together, and it really touches on what Eric was talking about, that as the needs for data have evolved and organizations are trying to tackle that problem of the 80% of their data that's unstructured and gain visibility into what they have, knowledge about what is that data with enriched metadata, and then put it to use, you need to unify it into a data platform that has the ability to create metadata, unify access, and then place the data with the applications. And so that's what Hammerspace does from a very high level. And then before I hand things over to David to talk about what we are announcing today, I think it's always nice to see kind of a less complex view of, okay, that sounds cool. There's a lot of technology built in. What is the experience? And what it really comes down to is users have seamless access to their data. They're on their laptop, they have a directory tree, they can see all the data that they have permissions to see that's sitting on their Isilon, their NetApp, their object store, and their cloud environment, for example. And it just looks like a directory tree. They can click on it, they can read, write, collaborate, and it's the experience that they're accustomed to with their file data. And it can be file or object. I'll mention that, and we'll touch on that more later. From an administrator's view, they have that single pane of glass to be able to see what is the performance of my overall environment. Are there mobilities of data that are going slow and why? So it's a really unified view of the data and the infrastructure to make it much easier to tackle this decentralized data, that unstructured data that's growing so quickly. Today, we're announcing a new capability, though, that up-levels this both on the performance as well as the efficiency side. So with that, I'm going to hand things over to David to talk about what is Tier 0.
So, yeah, let's start with the problem statement. What we have learned is that it's very common for folks to have high-performance flash storage, NVMe, inside of their compute nodes or GPU nodes. And that it takes, sort of unrelated but related, is the fact that once you deploy a GPU cluster, it's not uncommon, as Eric put it, for one to realize that, oh, we need the storage subsystem. And then you have to take the time to deploy to create a shared storage environment from that. So key things here, it's time to market is critical. As soon as the GPUs are there, the clock is ticking on getting value from them. And yet here we have storage that is trapped capacity inside of the DGX nodes. And that storage largely goes unused because it is difficult to manage little islands of data inside of each server, isolated from the others, and especially in large clusters where you have tens, hundreds, or even thousands of these, like some of our clients do. It's very difficult to get any utility from the local flash. That local flash can come in very large quantities. It's not atypical for those servers to come with 30 to 60 terabytes baseline built in that you can't even opt out of in the bill of materials. Moreover, there are slots for up to 8 NVMe devices in each of those. So what Hammerspace Tier 0 does is it allows you to orchestrate, place, and access data across that server local NVMe from a global network shared file system, and do that using the hyperscale NAS architecture with the control plane that sits off to the side. So here is a visual of that. What this does is it unleashes that stranded capacity that's sitting in those servers. And it allows you to improve ingest performance, checkpoint performance, transform performance, how fast you can manipulate the data sets that are going to be put into the GPUs, because now you can bring to bear the full aggregate capacity and performance of that NVMe flash across all of the GPU servers and all of the high performance networking that's used to connect them. And the cool part about this is it's very, very easy to deploy. The machinery needed to have the compute nodes be able to supply that storage to the shared storage space is all built in to Linux. It's simply NFS. With the Linux kernel NFS server, you can deploy it literally within minutes, announce it to the sideband control plane that is the Hammerspace Anvil, and then voila, it can be used to host data distributed across the environment. So
I
here
love it.
we have
Oh,
an example. Oh yes, Eric, go
I
ahead.
was just going to say, I love that. This tier zero, I think, is not just one of the most clever things that a company has come up with in quite some time, but it's an excellent description because everyone understands tier one, tier two, tier three, and you're now opening up what I call the fastest path to compute, right?
Yeah, and that's really one of the key differentiations because people have done software-defined storage for a long time, and people have done hyper-converged infrastructure. Tier zero is very different. Tier zero is part of a continuum. It contemplates, or it's based on the notion of data orchestration, and that data is able to move across a continuum from tier one, even tier two or tier three, even across to other data centers, but flow all the way and get promoted into the GPU servers themselves. Now, this is a perfect example. This is a real world example of a customer that deployed some external shared storage, some NAS storage, and yet had 50% more storage in the GPU servers themselves than the shared storage that they had deployed. And when they ran out of space on the shared storage, there was a realization that, hey, we've got all of this trapped capacity inside of the GPU servers. So by using Hammerspace as the data orchestrator, and by using the standard Linux machinery to put a local file system, the XFS file system in this case, and export it using NFS, using the kernel NFS server, that now becomes available space for the orchestration platform and increased the capacity by more than double. Now, let's talk about this as a tier in the greater spectrum. This is not an island unto itself, although you can, and let me emphasize, you could have an environment with nothing but tier zero. It is perfectly capable of being the entirety of the storage. But we're assuming a world where you do want to have cheap and deep capacity that may not even be flash-based. It may be disk-based. It may be tape-based. You might have on-prem or even in cloud S3 object store that is part of the tiering system, and the data flows freely. So one of the first differentiations between this and software-defined and hyper-converged is that this is part of a complete data environment. It's not an island unto itself with all of the challenges of being software defined and being co-resident with the compute, limiting how you can scale the storage. Here you can scale capacity independently of scaling the performance tier. Moving to the next slide. So with this, you're able to achieve some immense performance improvements. And there is no place as exemplar of this as checkpointing. Let's take an example of a customer that has the need for 100 petabytes of capacity and a terabyte per second of bandwidth to serve 1,000 GPU servers. That would be 8,000 GPUs with 128 terabytes of storage in each. Now, if you were to look at what it takes to checkpoint such a system, it is not uncommon for checkpointing to cause the system to stall for on the order of several minutes, hundreds of seconds. And checkpointing must be done every hour. Now, why do we checkpoint? Because things fail, especially when you have lots of components and burning really hot. So GPU servers can be less than reliable, and that means you have to roll back to a previous checkpoint and start over again so as to recover from a failure. Checkpoints are also useful to fork so that scientists can say, well, what if we trained from this point on using some different data? So checkpoints are also useful for some experimenting with alternate ways of training and so forth. But for this point, let's talk about it just in terms of work loss. And one of the key points is that if your checkpointing is done to tier zero, it can achieve the full performance of local access to NVMe while still being files on a shared file system. In other words, you get all of the benefits of local access with all of the benefits of it being shared file. And that allows the checkpointing to be brought down to mere seconds. And because of that, you can do it more frequently and lose less data when you do have to roll back. And those two things compounded means that you're talking about recovering on the order of 10 to 12% of the GPU compute time. Meaning that if I have an environment with these 8,000 GPUs, you effectively have over 800 GPUs worth of more productive output by not sitting idle on the checkpointing, much less on the ingest or on the transforming of data that you might do through the system. Any comments here, Eric, or questions?
I mean, I just think this is really remarkable, and I know we're going to hear from Trond in a minute about going into the actual kernel itself, but basically you've opened up a super highway for data movement by abstracting out all the metadata of the files, where they are, what their names are, which of course facilitates orchestration, facilitates discovery. I mean, you can't orchestrate data that you can't find, right? I mean, just the discovery side is such a challenge, right?
Indeed. So yeah, the way the orchestration works is by housing all of the metadata in the control plane so that the data can be routed and dynamic, allowing data to move, potentially even while it's being accessed. So let's move to the next slide here.
And as you do that, David, one thing I think worth mentioning is, you know, we do have some massive customers in Hammerspace and using tier 0. But a lot of companies might look at this and say, well, I don't have 100 petabytes or I don't have 1,000 nodes. With our linear scalability, I think it's worth touching on whether you have
indeed.
10 nodes or 1,000. The benefits are the same, just in the appropriate ratio to nodes. But maybe just talk about that a little bit for smaller GPU environments as well.
Yeah, both on a proportionate capacity basis and on the performance basis. And the interesting thing is it scales with proportion. Because this is within the GPU nodes themselves, as you put in more GPU nodes, you get more tier 0 performance in aggregate. And when you write checkpoints that are affinitized to hit the local media, I mean, it's logically been written to the shared file system, but it's physically being written to the local media on each node, you have perfect proportional scaling of performance. And because of the data orchestration, you can indeed scale capacity independent. You don't have to crack open the boxes to put in additional NVMe, although you can. So you have all of the flexibility of both, you know, a shared storage, you know, dedicated storage node environment versus the flexibility of, you know, economizing by using the existing infrastructure that's already there. Literally not necessarily needing to deploy any shared storage whatsoever by just sharing the tier 0 across the compute nodes. Now, let's get into more specifics here. If we look at how NAS architectures are built today, what you will see is why it's so important to move to parallel file system architecture. Here I'm depicting a NAS vendor that not supporting GPU direct. And you can see here how many times the data must be retransmitted across a bus, chip to chip, or across a wire to or from the networking. And in a scale out NAS systems, you have data nodes, the storage nodes at the bottom, and you have controller nodes that add the protocol. They add the file system. So the two boxes on the bottom are part of the storage, and the shared storage and the client obviously is your GPU server. So this is 10 data retransmissions. This is why NAS is not particularly well suited to serve GPU environments, but we get better by doing GPU direct. And you'll see in that top box a difference. The data is routed directly from the NIC to the GPU. So we depict that by taking the CPU root complex out of the path. And now we have gone from 10 to 9. So this is why all the hubbub around GPU direct. It allows the data to flow much more directly. You know, you go to 9 from 10. Now, if you use NVMe over fabrics, then you can go from 9 to 8. Look at the bottom box, because now the data can flow from the NVMe out the network without having to go through the root complex there. So we've disintermediated the root complex, not just at the client with GPU direct, but down at the storage server with the NVMe over fabric technology. That gets us to 8. But all of this is just rearranging chairs on the Titanic. That whole approach is what is broken. Now, if you go to exotic file systems like Lustre or IBM GPFS, they use this approach that you see here. They take the control path out of the data path. They have a separate control plane. And that is indeed what hyperscale NAS does, but using standard NFS. So you get all of the benefits of this being plug and play NAS, but you get the performance from the HPC world. And as you can see, it makes a dramatic difference. Now we've disintermediated the entire controller node. What in the vast parlance is the C node versus the D node, the data node. So this is why hyperscale NAS is such a different architecture. But what is interesting about this is that the storage node and the client have nothing but off-the-shelf Linux. There is no software loaded there, unlike, say, a Lustre or a GPFS, where you're having to put software in your client and software on the storage nodes. And it's heavyweight, bulky, it has to go deep into the kernel. This is just using the built-in data path that's inside of the kernel that's made to move data 0 copy and with RDMA capability. It's the NFS client to the NFS server. The entire data path, top to bottom, unadulterated Virgin Linux. Now, what that allows you to do is to fold it in on itself. So now the storage node is the client, is the storage node. The NVMe in the client is simply exported as NFS, and the client simply connects to the control plane and connects to parallel NFS to get the routing information. Now, if the data is located on a peer, then it will go out over the network to the peer using NFS and the machinery built into Linux. And it's extremely efficient because this is native code in the kernel. It's 0 copy and it's capable of RDMA. So you don't have the massive overheads of hosting a complex storage node software stack. It's very streamlined. So you don't have noisy neighbor issues. You're not occupying them because it's 0 copy moves. It's over RDMA. And very fast. But the cool part is when it's local, when the data orchestration system has affinitized data to the node or nodes using them, because it can run with multiple instantiations, one on each client, then you get the full performance of local direct access.